This lecture is going to focus on noise and occupational hearing loss. Before we start, we have to know a little bit about what noise is. And the first part of that is to know some information about the physics of sound. The important components of sound waves are the frequency, which is measured in hertz, Hz, or cycles per second, the amplitude, which is how much magnitude or pressure displacement is occurring with the sound wave, and the wavelength, which is typically measured in meters. This is a graphic of the relationship between the frequency, amplitude, and wavelength of a sound wave. And as you can see here on the bottom, the x-axis is the distance, so this is one wavelength. The amount of time that it would take to traverse that is going to relate to the frequency. And the amplitude is atmospheric pressure displacement. When noise is created at a source, what it's doing is displacing pressure, and that pressure is going to travel in a sound wave, which is represented here. And the magnitude of that pressure that's created is measured in terms of the amplitude. Now there's a relationship in sound propagation. The relationship of lambda is equal to c divided by f. That tells you the relationship between the wavelength of the sound, and this is going to be related to the rate of sound propagation c divided by the frequency of the sound f. And you can you can use this to determine certain characteristics of the sound wave if you're familiar with how fast the sound travels in different medium. In air, for example, sound travels 1,129 feet per second. And if you're interested in knowing how long it'll take for sound to travel 5,280 feet, you can divide 5,280 feet, which is a mile, by 1,129 feet per second, and you'll get 4.69 seconds. So when you were younger and you were told to see whether or not a storm was a mile away, what you would do is you would watch a flash of lightning, and then you would start listening for the clap of thunder, and you would go 1001, 1002, 1003, 1004, 1005, kaboom, and if you heard that, you knew that the storm was 1 mile away. So you've been applying this for a number of years, but this is how it actually works. Now when we are exposed to sound pressure on our tympanic membrane or eardrums, it's going to be, the sound waves or pressure is going to be pressing upon our eardrums in units that we can measure. It's going to be a unit of force per a unit of area. For example, pounds per square inch. We're used to that because that relates to what we're dealing with, putting pounds of pressure in our tires. But it's pounds per square inch is a unit of force per unit area. So is all the rest of these that are mentioned, which you may not be as familiar with, such as microbars or micropascals, but newtons per square meter or dynes per square meter are both units of force per unit area. Now, what we are dealing with sound pressure is a little bit complicated, because when sound pressure comes up against our ear, the quietest value versus, or in other words, the lowest level that we can detect audibly, versus how much it causes our ears to hurt, is 10 million times greater. So we have this huge scale of pressure variations that go against our tympanic membrane that are vary in magnitude by 10 million fold. So how are we going to design instrumentation to measure that? Well, this is done commonly in a lot of fields where you see differences between 0 or 1 and 10 million. What will happen is you adopt a logarithmic scale to make measurements a little bit easier. For example, in chemistry, if you go from pH of 6 down to pH 5, what you've done is change the hydronium ion concentration by a factor of 10. If you go from pH 6 down to pH 4, you've changed it by a factor of 100. That's a logarithmic scale when you're dealing with pH. Same with earthquakes. If you go in an earthquake, if you experience an earthquake of magnitude 6 and go to an earthquake of magnitude 8, the intensity that's experienced is 100 times greater. So that kind of approach is taken when we measure sound pressure due to the huge variations of sound that we'll hear over a typical workday type of exposures. Now the way that we measure sound pressure levels is by units called decibels. And what decibels are really are logarithmics, like I was talking about earlier with pH and the Richter scale for earthquakes, but we have a different spin on it a little bit for what we do for measuring sound. What we're looking at is the reference value, 20 micropascals. This reference value is the lowest audible level that the human ear can detect. And we use that as a standard against the P here, which is what's measured in terms of the actual sound pressure. So the sound pressure divided by the reference level squared times the logarithmic, take that to the log 10 by 10 is going to be what decibels are. So this is these are logarithmic terms, and it's important to remember that as we get into the next couple of slides on how we go about adding decibels and have 1 decibel source of sound versus another, how much more contribution will it be for the second source? Now, this is a scale which is called the required dynamic range of a postage scale to match capability of the human ear. Over here on the far left, we have numbers that go from 0 up to 150. And that's kind of typical. If we're going to be monitoring workplace exposures, we may get sometimes impact noises as high as 140 decibels. On the right, what we have is relating decibels to what it would be like if decibels were actually measured in pounds. And so we start at the bottom with the 6-ounce letter, and we end up at the top at about 144 decibels. That is 6,262,500 pound Saturn V rocket. So you've got that much variation that can occur in typical workplace measurements. And let's take an example here. Let's look at 90 decibels, about 99, where we have an 18-wheeler. And if we wanted to measure the 18-wheeler in terms of pounds, with or without the truck driver who weighs 200 pounds, it's not really going to matter that much if the truck driver's in there, because the 35,000 pounds is so much greater than the 200 that the contribution of this lower level is going to be minimal. And that's kind of what we have to do when we take into account adding decibels and comparing different decibel sources, is that the fact that one of them is going to be much, much greater than the other. 110 decibels is much, much greater than 60 decibels. This is the difference between the space shuttle, the weight of the space shuttle, and the weight of a motorcycle, going from 60 decibels up to 110 decibels. So it doesn't sound like that much of a difference if you go from 60 to 110 decibels, but if you think of it going from a motorcycle weight to a space shuttle weight, you can kind of get the idea. Now, how do we add decibels? I like to use the shortcut decibel addition, and one of the problems on your worksheet, which we'll go over on the board, is to apply the shortcut decibel addition method. And this is pretty simple, because if you have 2 decibels that you need to add, you need to do 2 things. First of all, you need to look at the difference between the 2 levels to be added. If it's between 0 and 1, you'll add 3 to the higher number. If it's between 0 and 4, you'll add 2 to the higher number. If it's between 5 and 9, you'll add 1 to the higher number. And if it's 10 decibels and greater, you don't add anything to the higher number, because, again, that's like weighing the tractor trailer with or without the truck driver. The contribution of anything that's 10 decibels less is not going to have any effect on the higher level at all. So, for example, if we want to add 83 and 83 decibels, first thing we would do is look for the difference between the 2 levels, and 83 and 83, the difference is 0. And then you add 3 to the higher sum, which is 83 plus 3, so you would have a final answer of 86 decibels. And think of this as like you have a room and you turn on a lawnmower that runs around at 86 decibels. And then you turn on a second one. How much louder does it get in the room? Well, it gets louder by a factor of 3 decibels, so it would go from 83 decibels up to 3 decibels. And you can use this in the problem set that I'll go through on the board. Another way to multiply decibels, which I don't teach and don't expect you to do in exams, but I want you to be at least familiar with and put this in your notes to use later, is the way to actually take advantage of logarithms. And so if you have want to add 2 different decibels, you would divide the decibel amount by 10 to get x. You'd take 10 to the x. You'd add 10 to the x and 10 to the y. That's your second number. You'd take the log of that and multiply by 10 to get your answer. As an example, here we have 83 and 83 decibels. Dividing 83 by 10, you get 8.3. So you take 10 to the 8.3 plus 10 to the 8.3 is equal to that large number there of 399,052,463. You would take the log of that number and get 8.6, and then multiply that by 10, and therefore the answer would be 86. Note, that's just what we did on the shortcut addition. The difference between the two is 0. We added 3 to the higher value, which is 83, and 83 plus 3 is 86. So you get the same answer, but the shortcut method, you can do it very, very quickly. The next part of the sound wave I wanted to talk about, since we just talked about amplitude, is the frequency. Now, the frequency for human hearing varies. It's, for most people, about 30 hertz up to 15,000 hertz. And this is a range that's pretty typical for human hearing aid range. We can break it into this frequency spectrum into octave bands, and where one wavelength is one frequency is exactly double another. And if you play instruments on the piano, phone rang, lost my train of thought. Anyway, I'm back. The frequency for human hearing is between 30 and 15,000 hertz. Now we have different scales that we use for the measurements of occupational noise exposure. We have an A scale, a B scale, and a C scale. And the A scale pretty much matches what the human ear actually hears, and so it's pretty predictive for hearing loss. The C scale will simulate the ear at high sound levels, and they both have some uses and applications in industrial hygiene, but I wanted to kind of go through this and explain it a little bit by starting here. This is a frequency spectrum. You can see down at the bottom we have a frequency. We start from about 16 hertz up until about 32,000 hertz. And just as a reference, about here in 20 hertz we have the lowest note on the piano, around 250 is middle C, about 4,000 is the highest note. So we're looking at a frequency range that goes from 16 up to 32,000. Now, what we note here is that for very low frequencies, so 16, 31, 62, etc., we have this big range of where it's called inaudible. And what that means is, in order for us to hear something that is 31 hertz, we need for it at least to be 60 to 80 decibels. Once it's above that level, we can start hearing it. So you could be listening to something that's at 62 hertz at 50 decibels, and you'd be totally oblivious that you're even listening to it until it gets up to about 60 or 80 decibels, and then you can finally start to just hear it a little bit. The same thing over on the far right, where we get into the ultrasonic type sounds. People will hear to about 15 to 20,000 hertz, somewhere into that range. But you can have sounds that are much at higher frequencies than that to get into the ultrasonic range. Most of the time, human beings are unable to experience sound in the ultrasonic range, and it has to be extremely high sound pressure levels before we can pick it up. My dogs, for example, are very different. They can pick up sounds in the ultrasonic range much higher than I can, and so sometimes I think they will hear something in the ultrasonic range that I can't, and they'll just start jumping up and barking at absolutely nothing for no reason whatsoever. But that's just what dogs will do. But this is species specific. Dogs and some animals can hear out in these ultrasonic ranges. Human beings, it's around 15 to 20 that it's cut off. But note the curve of this. Where we hear best as people is between maybe 500 hertz and 6,000 hertz. That's the range where, if you're ever doing any audiometry, audiograms on a person, and you're in the booth and you hear a sound pressure level of a frequency of 500 hertz, you're going to hear that almost immediately when the technician starts turning on the tone. You'll raise your hand and say, I hear it, at very low sound pressure levels. Same with 1,000, 2,000, 4,000, etc. And this is the range where most people talk. So our frequency, our sound perception and frequency is best where people are, where human speech occurs. At the low range, it's not that good. At the high range, it's not that good. But in the range of most human speech, our hearing is particularly good. Now, when we set up the A weighing scale, what we're doing is trying to mimic this. We're trying to mimic the range at which human beings actually perceive sound. Since they don't perceive sound that well in the low frequency range, we don't measure it on the A scale. Since they don't perceive sound all that well in the high ultrasonic range, we don't measure that. We just drop it off, because what we're interested in is sound pressure level at the frequencies that humans are most likely to hear. Now the C-rated scale is a little different. The C-rated scale, you can get vibrations that occur at very, very low very low frequencies. For example, if you've ever lived in an apartment house with cinder blocks and somebody's playing the stereo on the other side, you can hear the bass go through the cinder blocks, and that bass actually will have enough force to probably shake the pictures that you have hanging on your wall. And that's because the very low frequencies in the bass sound, even though humans can't hear them quite as well, they can still have energy and do damage. And so the C-rated scale is used in areas where you have very, very low pressures that have very low frequencies that have very high sound pressure levels that may actually do structural damage to something due to the vibrational forces that can still occur under those low frequency wavelengths. Even though you can't hear them, they can still do some damage. And that's what this is looking at. And this is looking at the A scale, the B scale, and the C scale. And I just want to focus on the A scale first. You've got my marker here on the A scale, and you note it goes from very low values here where when you have low frequencies, you'll see these minus signs because we're not measuring it. It doesn't matter. We can't hear it. It's not going to affect the human ear, so we don't measure it. So the A scale really is going to be responsive in the areas where the human hearing is best. And again, going back to the previous slide, the A scale mimics right in this area here where we have the best threshold of hearing. The C scale is pretty flat across the whole frequency spectrum. Even though we can't perceive the low frequency sounds very well, they can still do structural damage. So there are applications where industrial hygienists need to measure those frequencies because they can have very high sound pressure levels. And when the A weighting scale is used, you'll see an abbreviation called dBA. And you'll note here on the far right of this screen is the A-weighted sound pressure levels. And this is typical if you have like an accelerating motorcycle at 1 meter, 110 dBA. And that means this is how many decibels that are measured on the A-weighted scale. So those low frequencies are cut out, and this is really focusing in on the frequency spectrum that human beings can hear at the best. And this is just some examples of a few. I'll read one or two. A loud lawnmower at the operator's ear is 90 decibels. A normal male voice is 60 decibels. Air conditioning in an auditorium is 30 decibels. So that gives you an idea of the type of ranges of typical things that you may hear. The next topic I want to approach is how our hearing works. And this is entitled The Physiology of Hearing. And to address this, we need to know something about the conductive pathways, and we need to know a little bit about what composes our external ear, our middle ear, and our inner ear. This is a picture from your textbook about the sound pathway of sound conduction, showing all the different anatomical relationships. And what we're looking at here is sound is going to be conducted through the pathway of the ear canal. And it's going to come and press against the tympanic membrane, i.e. your eardrum. Once it does that, it's going to be exerting pressure on the three small bones of your middle ear. These are the incus, stapes, and malleus. And they basically act as a fulcrum. So what they're going to be doing is taking that air pressure that's being exerted against the tympanic membrane and multiplying it by a lever type action so you get a little bit more force. And then they will be pressing against the inner ear, which contains an organ called the cochlea. It looks like a big snail-like thing on the right, which is fluid-filled. So what you're doing is converting air pressure to hydraulic pressure by this particular mechanism of using the fulcrum of the bones in the middle ear. You'll note the density of the bone that surrounds the middle ear. It's the thickest in your body, and that's to try to protect these very, very small bones that are in your middle ear. They're very sensitive. If they're broken, it's very hard to heal them. And what occurs with sound transmission, the way sound will work is, again, you will have sound waves that will go, or sound pressures that will go into your ear canal, exert pressures on your tympanic membrane. That will, in turn, cause the three bones of the inner ear, the middle ear, the incus, malleus, and stapes, you may know them as the hamel, anver, and stirrup, to start exerting pressure on the inner ear, which is a fluid-filled structure. The fluid-filled structure of the inner ear contains a lot of hair-like projections that are capable of stimulating the cochlear nerve. So as the fluid is moving back and forth in a wave pattern of the inner ear, it's stimulating these fine hair-like projections, which will in turn send signals out to the cochlear membrane, the cochlear nerve, and you can perceive sound. That's the best I can explain it. I don't really understand how it works, how you can convert air pressure to what we're hearing, but simplistically, that's what's happening. Now, one of the reasons that it works so well is within the cochlea, we have a lot of these hair-like projections that are inside of these fluid-filled chambers. So as the fluids are moving back and forth, they're stimulating these hair cells. Of particular interest is over here, this organ of Corti. The organ of Corti has a lot of hair-like projections on it, and that will stimulate the cochlear nerve and send a signal back to the brain that helps you perceive hearing. Now, unfortunately, these hair cells are very, very sensitive and very fragile. And if you get into situations where they're overstimulated, i.e. by too much noise, what can happen is that they can break down. And when that happens, the damage may be irreversible. And so occupational hearing loss, and in particular what's called sensorineural hearing loss, because you're involved with the sensory perception of stimulating the nerve, is a very, very fragile type of a hearing process. And these fine hair-like projections that are in the organ of Corti can be easily destroyed, and if so, cannot regenerate, and you would have permanent hearing loss from essentially overstimulating them. And this is a close-up of it, what I was just talking about, the transmission of sound across the cochlear duct, stimulating the hair cells. This is a little bit better close-up of the organ of Corti, and you can see the fine hair-like projections that line this fluid-filled cavity. And again, they're very, very, very sensitive, and if destroyed, may not be able to regenerate. And this last picture is just sort of an overview of how the whole process works. And again, you'll have, starting on the left, you'll have sound pressure coming in through the ear canal, exhibiting pressure on the tympanic membrane. That in turn is going to cause movement of the small bones in the middle ear. And they're going to press against the fluid-filled chamber in the cochlea. And you're going to get the fluid moving back and forth in a pattern, stimulating all those hair cells. And when it does so, it will put out impulses to the cochlear nerve, and you'll be able to perceive hearing in the brain. Now, if you do an audiometric examination, and probably most of you have done internships where you've had to do audiometry and have an audiogram generated, what will happen is you'll be in a booth and you'll be putting on some headphones, and then they'll start, usually with each ear, putting out sound at a specified frequency. Typically, audiograms go from 500 to 6,000 hertz. And so you'll sit there in the booth, and once you are, the technician will start the test, and they'll put out a sound tone at 500 hertz, and they'll wait to see where you can hear it. So they'll start turning the dial up, and once you get to the point where you can hear it, you'll raise your hand, and they'll write it down that you've been able to perceive 500 hertz at so many decibel levels, and they'll repeat that throughout the spectrum. And when they do that, they generate an audiogram. And typically, if you are having employees that have to enter a hearing protection program, an audiogram needs to be done at least on an annual basis. Now, an audiogram will change over time. As you get older, audiograms will change due to a process known of aging, and this is called presbycusis. Presbycusis is a term that relates to age-related hearing loss. So presbycusis is age-relating hearing loss. There are several types of occupational hearing loss that can occur. And I wanted to go through each one of these and then show you some diagrams of how they would be represented on a typical audiometry test. The first is conductive hearing loss. Conductive hearing loss occurs when sound is not being conducted properly into the inner ear. This can happen in a couple of ways. For example, if you have earwax, then the sound is not going to be conducted into the past the tympanic membrane. You're not going to be able to utilize the bones of the middle ear, and you're not going to hear anything in the inner ear. Alternatively, you could have an injury. You could have a perforation of the tympanic membrane. a ruptured eardrum, in other words. And if that happens, sound cannot be conducted adequately into the inner ear. Or another example is you could have some kind of head trauma, and in so doing, break one or more of the bones of the middle ear. They're very well protected in a thick area of the skull, but they could still be damaged. If those are broken, that fulcrum action cannot be utilized to move the fluids back and forth in the inner ear. So anytime you have sound that's not being conducted into the inner ear, that is referred to as a conductive hearing loss. Sensoroneural hearing loss is something that's a little bit more specific, and it's what I was talking about earlier with the loss of those particular hair cells. With sensoroneural hearing loss, what's occurring is those fine hair-like projections are being broken down, usually from excessive noise over extended periods of time, and not able to regenerate. And when that happens, you will lose hearing at specified frequencies. And I'll show you some audiograms of that in just a minute. But there are usually some very typical areas where you start losing hearing first. The other type of things that I just wanted to mention are temporary and permanent threshold shift. If you go to listen to loud music for an evening and you come outside after you're done listening to it, your hearing may be a little bit fuzzy. If we did an audiogram at you at that particular point in time, it would be reduced from when it was normal. And if we did it the next day, it would probably be back to normal. So people who are exposed to loud noises, either on the job, they go to basketball games or loud concerts, their hearing is reduced a little bit after the event. And this is referred to as a temporary threshold shift. It's actually thought to be due to metabolic fatigue, in that a lot of those hair cells require energy, and you're depleting their energy faster than it can be restored. And so your hearing gets a little bit fuzzy, but after you've had a chance to rest, the next day it will be fine. If, alternatively, you have extended exposures to temporary threshold shifts, and you get to the point where the metabolic depletion is greater than your ability to restore the metabolic requirements of a lot of those fine hair cells, they'll die. And when that occurs, you have permanent threshold shift, and your hearing is essentially changed. You'll never hear the same as you did again, and an audiogram will show how that has occurred. And the last is acoustic trauma. There are situations where a very loud impact noise occurs, shotgun blast, a press hammer, flashbang, something that causes real loud noises really quickly that could actually rupture the eardrum, and that would be referred to as acoustic trauma. I wanted to go through some audiograms. Just the first audiogram, typical audiogram for a normal, healthy person whose hearing is in the normal range. And you'll see it's pretty flat. They're going from 250 out to 8,000 on this audiogram, and this is maybe 10 decibel variation, so it's pretty normal. It's pretty flat across the frequency spectrum that human beings' hearing is the most acute in. This is an audiogram showing conductive hearing loss, and if you'll note, across the entire frequency spectrum, we're reduced at least 20 decibels. And so if you had earwax, for example, somebody would have to yell a little bit louder because the sound is not being properly conducted in. And when you have conducted hearing loss, what you typically see is what's observed here. You'll see a decrease in all of the different frequencies, at least 10 to 20 decibels across the entire frequency spectrum. And this, again, exemplifies that for some reason, sound from the environment is not properly being conducted into the inner ear. And this could be due to a blockage in the ear canal, a perforated eardrum, a broken bone in the middle ear, a lot of different causes, but they'll all show this same type of an audiogram. This audiogram shows sensoroneural hearing loss, and this is typically what occurs in occupationally induced hearing loss. And what you typically see in this is a dip. This dip happens to be at 3,000. It's usually in the 3,000 to 6,000 range. But what it will refer to, what it will mean is that in that particular frequency hearing range, people just don't hear as well. And as I mentioned earlier, this is the range where human voices are. So people that typically start having trouble with hearing will, at first, there may be a voice on the radio, a child's voice, some person's voice that hits one of those frequencies that they just can't hear as well as they used to. And if they're exposed to the noise, this condition can get progressively worse. But sensoroneural hearing loss typically has a frequency that is much worse than the other, and it usually has a typical dip, as is exemplified in this particular overhead. Now, the next couple are going to show what worker exposures were for a control group versus a group that were exposed to different levels of noise. And what I want you to look at is the top line, the dotted line on the top, which is normal workers for that are exposed to normal type noises, versus the bottom group, workers who are matched and exposed to noises of 85 decibels. So you've got an exposed group on the top and a non-exposed group on the bottom. And the group on the top, it's not a flat audiogram like we looked at earlier, and that's because of this presbycusis. You note the mean age is 57. People tend to lose a little hearing as they age. But the bottom, if you're exposed to 85 decibels of noise, your hearing is much worse than the top group of controls. Now, what happens if we go to 90 decibels? That gap gets greater. You know, it was not that huge between the control group and 85 decibel group, but we get to people who are exposed to 90 decibels and compare them to a non-exposed group. Their hearing is much, much worse, and it's getting really bad around the 4,000 hertz range, which is down here by the number 4. Now what happens if we go to a louder noise level? Let's go to 95 decibels. And by this time, the people are essentially deaf. It's going to take 50 decibels of boost to get them to hear the sound properly. They're dropped down that far, especially around 4,000. So this shows you a couple of things. It shows you that the dose is going to influence the amount of sensorineural hearing loss. As we've gone from 85 to 90 to 95, the response has gotten much, much worse for exposures to those levels, and that it typically has a dip, and in this case it's about 4,000 hertz where the most of the sensorineural hearing loss is occurring. Now, losing your hearing really isn't the only thing that noise can do to you. Hearing loss is obviously one that we want to try to prevent as much as anything, but there are some other things that can occur as well. For example, if you are exposed to loud noises for extended periods of time, you may have other physiological effects, and these could be manifested in things as stress. That if it's in a noisy environment, it may be stressful, and stress can actually increase your blood pressure, so this kind of thing can happen. Alternatively, if you have to yell a lot because it's really noisy, you can be like some of the rock stars that have to have vocal polyps removed because of you're having to shout a lot more than a normal person would. Another problem with noise is communication interference. If you are in a noisy environment and you're trying to communicate with someone else, unless you have some kind of a signaling system worked out, it's very difficult to communicate verbally with loud noises in the background. And nonetheless, it just can be annoying. It can be add to the stress by having an annoying type of an environment where you have where it's noisy all the time. So hearing loss is not the only effect that can occur from noise. There are other effects as well. Some of them can be measured physiologically, like blood pressure. They can lead to health effects, like voice polyps. And they can be serious if you need to communicate with someone and it's noisy in the background. That may be very problematic. I wanted to make you aware of some of the regulations that are dealt towards noise. OSHA regulations are found in 29 CFR 1910-95. They rely on doses and doubling rates. I'm not going to get into how to do those calculations in this class, but I at least want to make you aware of them, that OSHA does rely on a dose determination. And, for example, these graphs talk a little bit about how the permissible noise exposure for determining the need for engineering and administrative controls or the need for a hearing protection program. And it's based upon the duration of exposure versus the sound pressure level that you're exposed to. So it takes into account the both the sound pressure level and the time. So these are essentially dose determinations. The other thing that I really wanted to make you aware of as well is that OSHA is not the only agency that has noise regulations, and you need to know that if you go into different sectors that are governed by different agencies than OSHA, the noise standards may be different. And even within OSHA, they're different between construction and manufacturing. So you need to be aware that there are differences in construction and manufacturing among OSHA. But if you get into mining, the calculations and the regulations are different. If you get into transportation, they're different. If you get into the Department of Defense, they're different. And I don't expect you to know all these specific numbers, but I do expect you to appreciate that there are differences in the regulatory approach by different agencies to noise level exposures. And this slide just tells you a little bit about the communication interferences and gives you an idea on how sound pressure levels, how much you're going to have to shout at different distances. If it's 98 decibels, you're going to have to shout a foot away. If it gets down to 71 decibels, you're good out to 13 feet, etc. The next section that I want to talk about is how do you measure sound pressure levels. And there's a couple of different instrumentations that are available that will do some of these measurements for you. Specifically, sound level meters, dosimeters, sound intensity meters, and narrowband analyzers. This is a sound level meter. It's a type 2. What that refers to, you have type 2, 0, and 1. Type 2 is a field instrument. Type 0 is a research-only instrument. So there are varying levels of sensitivity that these will have. But type 2 sound level meters are real common for industrial hygienists to go out and measure peak values in particular and average values of what exposures are going to be. If you pointed it toward a lawnmower that's going, you might get a measurement on your scale of 90 decibels in the A scale. So it can give you a real-time measurement of sound pressure levels using a sound level meter. The next is a dosimeter, and if you want to determine what the noise dose is so that you can see how you compare with what the OSHA standards are, this will give you essentially an average, but remember you're dealing with decibel numbers, but it will give you kind of an average level of exposure over a specified time period. And most of these do the calculations for you, so you can put them on workers and an environment, you know how much time they're exposed to, and you can get a comparison between what the dose is that the worker actually got versus how it compares to OSHA federal regulations or ACGIH recommendations or some other type of source. This is a sound intensity instrumentation system, and what's nice about a system like this is it not only gives you the sound pressure level, but it gives you a directional vector as well. So you can use this to map out if you're concerned about not only how much sound is actually present, but how much sound is present from varying directions. You can use this instrument to map that. So in the east corridor, it may be 95 decibels. South of the noise source, it may be 65 decibels, etc. You can get a directional vector using a sound intensity instrument system. And in some cases, that may be very, very helpful and useful. And the last is an integrating sound level meter. This uses octave band analysis, and why these are particularly useful is that certain sound sources are not going to be equal across the frequency spectrum. They may be very loud at 4,000 hertz and very low at 500 hertz. And so an integrating sound level meter will give you the sound pressure level at specified frequencies. And this could be extremely useful in selecting the proper personal protective equipment for protecting against that sound pressure level at that specific frequencies. And we'll talk in just a minute about controls, but all the different earplugs that you buy and all the different earmuffs that you buy are going to be rated on sound attenuation at specified frequencies. So if you know what frequencies are most likely present, you can select the correct hearing protection to protect against those frequencies. And the only way to do that is to measure with an instrument like a integrating sound level meter. Another point that I want to make about any of this information is it has to be calibrated, and calibration can be somewhat expensive, but to get an accurate value, you do need to calibrate it, and so these things need to be calibrated fairly often. We have a sound level meter in our IH lab across the hallway, and it does need periodic calibration. And this is just a sample sheet of doing some noise mapping. You would enter some data on sound pressure levels, some information about environmental conditions, information if you have it on octave bands. If you have an octave band analyzer, you could write down what the sound pressure levels were at 500 hertz or 2000 hertz, etc. Now the last part that I wanted to talk about is control of noise exposure. And you can control noise exposure by controlling noise at the source, controlling noise at the path, or controlling noise at the receiver. This is a comprehensive type of a slide that tells you all the different approaches that you can use to control noise. You can control noise at the source. And what can you do at the source? Well, you can enclose it, and so that the sound isn't getting outside of the source. Or you can put on vibration mounting so that it isn't quite as noisy. So there are several things that you can do by controlling noise at the source, even changing it with something that's not quite as noisy. So that's one of your first ways you can control. The second thing you can do is control the path. One of the things that's easy to do in many circumstances is increase the distance between the source and the receiver, make the path longer. And the longer the path is, the less sound will reach the receiver. Alternatively, you can do some other things with the path. You can put in some acoustical material that will either reflect or dampen the sound, and so the selection of materials can be very useful in attenuating sound from the source to the receiver. There's a lot to this field of acoustical engineering. It's really the same type of principle in designing a really, really good auditorium to listen to music. If you've been to the Carson Center in Paducah or the TPAC down in Nashville, where you can sit in an auditorium and listen to music, and almost every seat is going to have equal sound experience. That took some work in engineering on properly selecting the right type of acoustical materials. And you can do it the opposite way of trying to properly select the right acoustical materials so that not much of the sound of those specified frequencies are going to reach the receiver. So acoustical engineering can be very useful in this as well. And again, you can enclose the sound source like we did on the first. That can help as well. And then there are things we can do to the receiver. One of the things we can do to the receiver is put the receiver in an enclosed booth so that the sound is not going to reach them. If you can't do that by isolating the receiver or the worker in some type of an enclosure, you may be able to rotate them to reduce exposure time by changing job schedules or something like that. But if you can't minimize exposure by that, again, the last thing we ever want to do is rely on personal protective equipment, because with reliance on personal protective equipment, the hazard's still there, and now you're relying on somebody to use it properly. So you want to try to do these other things first, and if you can't, then you'll go to the personal protective equipment. When sound pressure levels in the A scale are over 85 decibels, you need to have a hearing conservation program. And each hearing conservation program is going to have some common elements. And these elements are as follows. Exposure evaluation. You need to go out and do measurements and determine how much noise is present in that particular environment. The second is engineering controls. Look at some ways to try to reduce the noise that's hitting the receiver. And this could be some of the things that we just talked about. Increase the path, use acoustical materials, substitute out the noisy equipment for something else, etc. So some type of an engineering control. The third is an audiometric examination. Typically, these are done pre-employment and at specified time intervals, either annually or 6 months after the employee is working, to make sure that they're not suffering from occupationally induced hearing loss. The fourth is employee education. Let people know what's occurring by loud noises. Let them know that this can be prevented by the proper use of some of these elements of a hearing conservation program so that they buy in to wanting to protect their own hearing, and educate them on things that are occurring off the job that may contribute to their hearing loss as well. And the last is hearing protection. If you're in a hearing conservation program, hearing protection needs to be available. And again, you want to try to engineer out the problem if at all possible, but if it can't be done, then hearing protection needs to be utilized by employees. You go to hearing protection, what are your choices? Well, they're somewhat limited. You've got earplugs, earmuffs, or helmets, and that's really about all you can do for hearing protection. And this is some typical types for earplugs. There are a lot of different types. Earmuffs, there are a couple of different types, and you can have acoustical helmets, and I have a recreational and a military one on this particular slide. What's important about any type of hearing protection is that it's used properly. A lot of times you'll see people use the foam ones, and there are instructions on how to use the foam ones. You compress them, insert them in the ear canal, and let them expand. But you'll see people put foam ones on just sticking out their ears, and really you're not getting much sound attenuation at all. So if any of these are going to be utilized, they need to be utilized properly. The other factor is selecting the proper hearing protection for the noise exposures that are occurring in your particular environment. And most of the earplugs or earmuffs you're going to buy have been tested to determine where the sound attenuation occurs. And what you need to do is match it. So if you have if you have sound that is present at 300 or 3,000 hertz, you want to get earplugs that are going to be effective against 3,000 hertz, and you can obtain that from the manufacturers. The last thing that I wanted to mention is, let's say you are in a real loud environment and you want to do everything you can to make sure that that sound doesn't get into the inner ear and cause potentially noise-induced hearing loss. Well, you could wear earplugs, and you could wear earmuffs, and then you could put a helmet on. But you still may get some sound hitting the inner ear. And the reason for this is that bone and tissue can also conduct sound. So, for example, if you're standing next to the space shuttle as it takes off, and it's 200 decibels, and you're wearing earplugs, and you're wearing earmuffs over those, and you're wearing a helmet over that, you're still going to be experiencing 150 decibels of sound, which would be enough to traumatize your inner ear, because the limiting, the most that you can get from the use of personal protective equipment is 50 decibels of protection. And the reason for that is you still have a bone and tissue conductive pathway. And if the bone and tissue are vibrating, it can reach the inner ear, as we can see here along the top line. You can go directly into the inner ear from bone. This is actually taken advantage of. There's a new piece of equipment for swimmers called a Schwimp, I think it is, that you can wear in the water. You attach a little probe to your head, and you can go swim away and listen to music. And what it's doing is taking advantage of bone conduction. So bone conduction is real, and again, the most maximum attenuation that you can get from any type of hearing protection is 50 decibels. And the last is just where can you have really loud noise exposure? Well, on aircraft carriers, for example. And this is my nephew and I on the USS Yorktown in Charleston, South Carolina one day, and we were looking at, this is a museum, looking at the old aircraft carriers there. But the reason I have this up here is that most people that work on flight decks are going to experience noise-induced hearing loss, because those airplanes are much, much louder than you can protect against by the use of any type of hearing protection. So the military usually has a rotation schedule for people working on flight decks to try to minimize the amount of time that they're going to be exposed to such loud noises. And that concludes my talk on noise. And if you have any questions, be sure to send me an email. Thank you.